Good afternoon. This is Professor David J. De Los Reyes. My topic this afternoon is a very interesting topic. It is miscellaneous volumes under integral calculus. Okay, let's proceed. I am now on lesson number 78 on my channel under the topic integral calculus, subtopic volume. It is the last topic under volume, miscellaneous volume. Miscellaneous volumes. We are now through with circular disk method of computing volume, hollow cylinder method, and the circular washer method. And the fourth method is actually miscellaneous volumes. Miscellaneous meaning it does not fall under circular disk, hollow cylinder, and circular washer. Miscellaneous. The configuration of this will now be 3D. We are already in space. We are involved in the XY plane, YZ plane, and the third plane. So actually we are in space, miscellaneous volumes. Okay, let's proceed. The problem is this. Find the volume of a right pyramid. It's a pyramid with a square base. The side is A and the altitude is H. If you have gone out to Egypt, at least you know what is a pyramid. The pyramid of Egypt is actually, I don't know if the base is square, but assuming it is square, the configuration is something like this. Okay? This base of the pyramid is A, square base. This is A, and A. It's a square base. Okay? And from the center of, from its altitude, you connect these points, you connect these 4 points here. So what will come out is actually a pyramid. The area of the base is square. This is A, and this is the altitude H. Okay? And by using integral calculus under miscellaneous volumes, try to compute for the volume of the pyramid. Because actually, in the so-called construction of the pyramid, we need cement, okay? We need concrete. So you need what will be the approximate volume of concrete, which involves gravel, sand, and water. So actually, this is now an application of integral calculus in the computation of volume in real life. Okay? Okay, let's try to draw the figure of the pyramid. This is the y-plane, y-axis, x-axis, and this is the z-axis. We are now in space. We added the z-axis. So you assume that you are on the corner of a room, okay? And you are in a corner of a room. Okay, I'll show you something like this. If you are in a corner of a room, okay, the first plane is the first wall. The second wall is actually the next wall, okay? And the floor area is actually another plane area. So actually you are now in space. You are not only on the plane. You are already in space. So you must have to specify your distance from X, from Y, and from Z. Like if you are hanging from here, you must have to pinpoint your accurate exact location. You must have to indicate the value of Y, X, and Z to pinpoint your exact location in space. Okay? So I draw this one. This is the y-axis, y-axis, x-axis, and this is the z-axis. And if we now try to figure out the pyramid, the base is actually square. So this is A, this is A. It seems we are on the floor section. Okay, we are. This is the floor section already. This is the first wall, and this is the second wall. The third wall is actually the floor area. So actually we are now in 3D, like okay, you've seen the movie 3D animation, okay? We are now in space. Okay, if we try to specify the coordinates of this one, it should be A0. This one, it will be A0, considering the Y and Z plane. Considering this plane here, okay, the coordinates of this one is A0. This one. The other wall. Considering the first wall, okay, the coordinates of this one is actually A0. But we got a problem here. The tip point of the pyramid is not on the Y plane. No, it's not in the XY plane. It's not on the YZ plane. And it's not on the XZ plane. It is in space. So actually, if we try to place the coordinates of this one, you see this one, this is 0, it's 0, meaning it is in space. Okay? The vertex of the pyramid is in space. It got three specifications: the value of X at this point, the value of Y at this point, and the value of Z at this point. On this one, we got only two because we are on the X line. It's only A in 0. On this one, we are only on the Z line, so it's only A in 0. Okay? This one, this one is actually in space also. But unluckily, it is on the floor area. So actually, it got three specifications also. It got the value X, it got the value Y, and it got the value Z. It's in space. Okay, including the vertex. Okay, let's try to bring out the differential volume. If we try to consider this wall here, the second wall on this portion, on the YZ plane, considering the YZ plane. If we try to consider for the meantime the YZ plane, okay, this side here, this will be the configuration of the differential volume. This is X, this is Y, okay, now this is Z, this is Z, this is X, and the thickness is dy. This is the thickness. It corresponds, or it goes in the direction of the y-axis, so it should be dy. It is dy. Considering the xy plane, the first side is x, the second side is z, the thickness is dy. So actually, differential volume is a variable square of thickness dy. Okay, let's try to compute for the differential or the base area. The area of this. What you can see. Base area will be the product of x times z. So this is actually xa. But from the given condition of the problem, the pyramid is a square. So meaning this side here is same as this one. So I will place it here, x is equal to z. The variables for the meantime, since we are on the YZ plane, it will be x and z, okay? Okay. Right? Wow. If x equal to z, this will become z times z, or the area of this, we call this a base area. It is z squared. As a function of the variable z, equation number 1. Then find the relation of z as a function of y using the YZ plane. We consider this line here. We consider the next wall, the line over here. It is this. Okay? We consider this one. So actually, if we try to get the coordinates of this line here, this one here, considering the YZ plane, it got only two specs. It will be 0 in x. This one here is z in y. This one here is in a0. Actually, this is alpha and this is alpha. I will bring out two right triangles. This is the first right triangle, okay, considering the upper one, and considering the bigger one, this will be the right triangle. So actually, considering the big, smaller right triangle, 0 and h, this is 0 and h, this one here, this is A0, okay. The smaller right triangle is ZY, this point is ZY, and this point here is A0. So it's just a matter of, if we try to compute for this one, it will be h minus 0. So this is h minus 0. Considering this side, it will be 0 minus a. Considering the next right triangle, ZY, this is A0, the vertical one will be y minus 0, and the horizontal side will be z minus a, z minus a. Z minus a. This is z minus a. Then alpha, take the tangent of alpha, h minus 0 over 0 minus a equal to y minus 0 over z minus a. Okay? We get the relation of z as a function of y using these two right triangles. And it emanates from taking the equation of the line consisting of the yz plane. Okay? If we try to compute for z here, z is actually a minus a over h times y. This is equation number 2. But if we try to look at back equation number 1, we need the value of z squared, so we square this one. If we square this one here, we simplify first, it will be a over h, quantity h minus y, all quantity square. Therefore, c square will be, the square of this will be a square over a square, and the square of h minus y is actually h square minus 2hy plus y square, equation number 3. So actually, we are now given relation of z as a function of y. Okay? So if we get the volume of this one, take the base area times the thickness. It is this. Base area, the variable area that it goes up from the base up to the vertex is actually variable. It is actually b times dy. But b is actually z square. But what is z square? It is a square over h square times the quantity h square minus 2hy plus y square times the thickness times dy. So this is now the differential equation. Okay? Differential equation that involves, differential volume as a function of y. So to take the volume, the variable volume, take the integral of both sides. The integral of the differential volume equal to a is constant, h is constant, it goes out. A square over h square, the integral. Our limit is from 0 to h times the quantity h square minus 2hy plus y square times dy. Why the limit from 0 to h? Okay, try to take note. The variable area should move from the base to the vertex, right? It is along the y-axis. So the limit is actually from 0 to h. Okay? The initial value is 0 to h. So the limit of the integral of the right hand side is from 0 to h. And the integral of the right hand side, easy money, guys. H square is constant, so this should be h square times y. This is 2h times y square over 2, or simply minus hy square. Power formula, the third one, y cube over 3 with the limit from 0 to h. Okay? Easy money. Put h in all y replaced by h, it will be h cube minus h cube plus 1/3 h cube. Okay, that is the upper limit. For the lower limit, it will now be minus 0. Because this is y, this is y, this y, it involves multiplication. So if y is 0, these three terms here, when 0 is put, or when 0 is substituted, it will be 0. The value of the lower limit will be 0. So actually, this cancels. Okay? H cubed over h squared, that will be h. Okay? There is an over 3 over here. This is 1/3 a squared h. So the volume of the pyramid as a function of the base a and h is actually 1/3 a squared times h. Oh, that's it. That's the solution. Try to imagine yourself you are in space. It does not only involve xy plane. There is an xy plane, okay? There is a yz plane, and there is an xa plane. It seems you are in a room, okay? The first wall is actually the xy plane. The next wall is actually the yz plane, and the floor area is actually the xa plane. We are already in space under miscellaneous volumes. Try to imagine that one. Okay, that's it, guys. That's an example of miscellaneous volumes. You must know how to set up your base area from the figure, and you should graph your figure correctly on the x, y, and z plane correctly. Because if the graph is not correct, and the formulation of the relations, you will be wrong. But as long as you graph it correctly, okay, the relation will be correct. So I will repeat it for the last time before I go this afternoon. Volume for a square pyramid with altitude h is 1/3 a squared times h. Okay, good afternoon, Los Angeles.